Hey, once again, it is physics time, and this time we are talking about electric fields. Electric fields. It's not a field where you go and play soccer and you get an electric shock, because that would be stupid. Electric fields. Four things really you need to know about. You need to know about the force on charges. You need to know about the electric field strength, E. You need to know about work done when you move one charge closer to another or further away from another. And you need to understand electric potential. Four things. Four things. So let's start with Coulomb's law, the force law. So, if you've got two charges, big Q and little q, they will attract or repel each other. There will be a force due to their charges that acts through space instantaneously, and that force is directly proportional to the size of each charge, so Q and little q, and it's also inversely proportional to the square of the distances they are apart. Meaning if you double the distance apart, the force is it's not going to halve, it's going to drop to a quarter. If you triple the distance they are apart, then it's not going to once again, it's not going to halve, it's going to change. It's not in direct proportion, it's not an inverse proportion, it's an inverse square proportion. So what we have is this relationship here, the distance squared, and there's of course a constant of proportionality. So force is directly proportional to one charge multiplied by the other charge divided by the square of the distances. The constant of proportionality, well, we could be really straightforward and just call it K, but why don't we make it a whole lot more complicated by that? Let's call it 1 over 4 pi, another constant called epsilon naught, which is the absolute permittivity of free space, and it happens to be 8.85 times 10 to the 12, 10 to the minus 12, so it's a very small number. But now you can sleep at night because you know this is the absolute permittivity of free space, and your life has now changed. So this is Coulomb's law. Force is directly proportional to charge 1 times charge 2 divided by the square of the distances, and that's the constant. Okay, so the forces occur on charged objects because there's an electric field. The electric field is the force per unit charge. So E equals force per unit charge, force per coulomb if you like. Now because we already have a formula for force, and here it is, you can very easily simplify your electric field formula to, well, not simplify it, you complicate it in a sense, but force divided by charge just becomes all of this, take away one of the charges. So we say it equals, once again, 1 upon 4 pi epsilon naught times Q over R squared. Because you divide force by charge, that takes care of little q. Gone, wiped out. Now, that's just a bit of maths for you. Let's just have a think about what's actually going on. When you've got two charges, it doesn't matter what size they are. Let's just say in this case one charge is negative. It could be negative anything, negative 200 coulombs, negative 50 coulombs, whatever. This is a positive charge. Let's think about what the electric field is actually doing in any region in space around these two charges. Well, electric field is always the direction of force on a positive charge. Think of a 1 coulomb charge placed here. If you place a 1 coulomb charge here, it's a positive 1 coulomb charge. It's going to be repelled by this guy. It's also going to be attracted by this guy, but he's so much further away, and distance is the relationship depends on the square, the inverse of the square of the distance. So that guy's going to have very little effect. So there's going to be an electric field line heading straight outwards. Same here, straight outwards, straight outwards. From here, the direction of force on a positive charge is going to be straight towards him. That's pretty simple. And direction on a positive charge here is going to be inwards towards the negative. And of course, if you put a charge here, it's going to be drawn that way and it's going to be repelled this way. So you end up with a pattern that looks something like this, which looks really familiar because that's the same sort of pattern you get around a magnet, but for very different reasons. So we need to be able to understand how to draw electric field lines. The closer the lines are together, the stronger the field is. Strong here, weak out here, strong here. And the field lines can never touch. If they do touch, you go to jail because it's just illegal. You can't have them touch. The closer they are together, the stronger the field. So they must never touch, because if they were to touch, that would imply an infinite field. And if you had an infinite electric field strength, that would blow up the universe. And for that, you really must go to jail. So now we have a work done. Let's consider work done. So we all know work done in any situation is equal to force times distance moved. Let's call distance moved r today, because r is the symbol we're using for the distance between two charges. So it's really quite simple to see that if work done equals force times distance, and the distance between the two charges is r, go back to this formula here, and you've just got this 1 upon 4 pi epsilon naught times charge 1 times charge 2 divided by r squared times r, the distance. So the formula becomes pretty straightforward. Well, I'll write it out again, I suppose. So it equals 1 upon 4 pi epsilon naught charge 1 charge 2 divided by r, because you're just multiplying this by r. That is your formula for work done. It doesn't stop there. There's another thing we need to know too, that is electric potential. Now the electric potential is the work done when you take a positive unit charge, 1 coulomb, and you take it from infinity, where it just happens to live, and you bring it to a certain point. Now it's a weird sort of concept, but it's very similar to gravitational potential. So in this case, electric potential simply equals work done per charge. The electric potential equals work done per charge. And if you want to think about potential difference, which is what we're more used to, potential difference is delta V. It equals the change in work per unit charge. Now again, that you can just substitute this in, and you get a for each of these formulas you can see that they're very similar to each other, and it's very easy to get them confused, so you do need to learn each one to make sure you know when to apply them. Okay.